Okay, so this will be equal to what? So those will be negative, and I flip the transfer function up top. So 4 divided by that, so it will be something divided by 4. Now I have two poles, a pair of complex poles. I can plug in any one of them. So I can choose just the one with a positive imaginary part. So be minus, so this one times, I'm sorry, plus 2 be minus 0.5 plus j 2.5. And this whole thing plus 3, so it'll be positive 0.5 plus j 2.5. Okay. So remember, you only plug in one ball, not both of them. If you plug in both of them, you will run into some calculation error. So going forward, let me put this negative 4 here, and if minus 0.5 plus 0.5, so minus 0.25. If j2.5, j2.5, that will be minus 6.25. Okay, since j squared is negative 1. And it's minus 0.5 times j 2.5, and plus 0.5 times j 2.5. That two pure imaginary numbers, imaginary parts will cancel each other, and you should have just 2.45 divided by 4, or it will be 1.625. Okay, 1.625. So this will be your k, such that you can have this 5% or 4.3% of overshoot. Let's check the static tracking error. How do we calculate this again if you don't remember? The equation we have is in chapter 7 is like this, where g is the open loop transfer function, but here we have gh, so it's probably better that we write it as gh. And you can plug it in easily. So when you have k involved, sorry, go back, should be multiplied by k as well, since we have k involved. So when you have this 1 plus k, we calculated is 1.625 times 4, and then 2 times 3. So this is the s plus 2, s plus 3, and s equal to 0, as we have here. 1 plus, and you have 6.5 divided by 6, so 6.5 divided by 6. And you don't really have to use your calculator. 6.5 divided by 6, just a little bit over 1, somewhere close to 1.1. Plus 1 will be 2.1. 1 divided by 2.1 is just a little bit less than 0.5. It's nowhere within 0.1. You can easily check this is. And what does it mean? It means if you use a P controller in your system, okay, here we only try the P controller, then although it's possible to achieve the overshoot by choosing k appropriately, which is 1.625, this number's never going to be enough to give you a good static tracking error even to unit step input. It's going to be larger than 10%. It's actually close to 5%, to 50%. And what we do? Well, again, there are multiple ways you can try, but we'll discuss this in chapter 7. If you really want to have some steady state tracking error performance, you should think about using a PI control. So that's something that we're going to try. But when you have a PI controller, you basically have two parameters. And determine two parameters simultaneously can become rather complicated, right? You have 2 degrees of freedom. You have to see how the two parameters interact with each other, and that's not really convenient. So the typical approach that control engineer or designers usually do is as follows. Well, we divide and conquer. We first use locus to find the parameter of repeat control, so that the transient specs are met. And when we do that, assuming a P controller is used. So basically what we just did above. And the second step is, after we find this P, the gain P, add an integral term, and choose this Ki, usually small enough because as soon as you add this I term, your static tracking error to unit step input is going to be 0. So you have achieved that goal already. But by adding that I term, it may compromise your transient performance, so that you want to come back and make sure your transient performance are not affected. So you want to choose the Ki small so it doesn't really have major impact. So that it does not affect transient behavior. Well, it's going to affect anyways, but just as long as it's not too much. You're not having too much deviation. Otherwise, you have to redo the design with 2 parameters involved. But now if it's not too much, you can just fine-tune the other parameters in order to find a good way to have it. So mathematically, this is what we usually do. Right, Kp plus Ki plus over S. And of course we can write it as Kp S plus Ki over S. Or we can even do this. We can do Kp times 1 plus Ki over Kp times 1 over S. Right? We can write its transfer function. Now, instead I want Ki to be small enough. It comes down to this term. And when people usually do the designing, you want to choose this ratio rather small enough, as we have up there. And you can, start with numbers like 0.1, 0.2, and so on. Just don't make it too hard. You can make it even smaller, but 0.1, 0.2, 0.3 are usually some good choices to start with. Okay, so this is how we do the control design. Now, coming back to this example again, if I use this control, now let's assume this is what we do. We choose Ki over Kp equal to 0.3 for this example. We can do this, no problem. Then the open loop transfer function becomes your controller kp1 plus 0.3 divided by s, so this is my controller, times 4, and divided by what we have earlier, s plus 2, s plus 3. And we can reorganize the term. Right, you have this integral term s, so we can move it down. So it'll be s plus 2, s plus 3. And then on top you have 4k. This will be s plus 0.3. So I multiply s on both sides of the equation, so this is what we have. Now when you view this, this is slightly different from what we have in typical root locus. In the typical root locus, you don't have a 4k in front. You usually have just k in front. Okay? We usually just have k involved. In this example, we just have k involved, but now you have 4k, but it doesn't really matter. Doesn't really matter. One way, if you want to make things easier, you can say you take this, view this as k, a big k, and then just divide by 4, eventually have this kp parameter. Now, how we do the root locus for this one? Easy. Find the poles and zeros again. You have 3 poles at the origin. And I have 1, 2, -2, and then -3. 0, you have 1, 0 at 0.3, so I'm going to have that here. And that's it. And now you can do the real section, which will be here, and it will be here. And you have 3 poles, 1, 0, so you have the order difference being 3, and that means you should have 3 asymptotes. I'm sorry, the order difference is 2, yes, 2 asymptotes. And the angle, since 2 of them will be 90 degrees, and minus 90 degrees. And the centroid being the sum of the pole, 0 minus 2 minus 3, so minus 5, and minus 0.3, divided by 2 still. Divided by 2 still. So you have minus 5 plus this would be 4.3, and it divided over, so it will be negative 2.35. Now, and now you can even compare with what we have above. When you have a pure P controller, the centroid is at negative 2.5. Right here, we have negative 2.5, and goes, the asymptotes have the same 90 degree, negative 90 degree angle, and the breakaway is at negative 2.5 already as well. But if you add this new 0 at negative 0.3 here, although the asymptotes still have the same angle, but the centroid got shifted towards the origin from negative 2.5 to negative 2.35. So you're actually looking at the asymptote closer to this. Closer to that. And you can still do similar things as to calculate the breakaway point, for instance. And for the sections, we know it's going to go this way. But the breakaway can be, two possibilities. One possibility is it may go like this. This is one possibility. Or the breakaway may go from the other direction, but go like this and go like this. Without calculating the position of the breakaway point, both are possible. Both are possible. But when it comes to control design, it's not really that important, right? It's not really that important. We know that to do the control design, especially when you look at the overshoot, we just look at the angle, 5%, will be tuned down to 4.3% such that you have this 45 degree. And you'll find intersection, either there or there, doesn't really matter. Either here or here, doesn't really matter. You still want this to be the 45 degrees such that you have the overshoot being about 5%. So still choose this being square root of 2 over 2 such that the angle 45 degrees is I mentioned. Okay. And when you do the sketching, you should be able to find this approximately such that you can calculate it. That's all the essence of locus approach. It doesn't require very precise calculation, just give you a starting point. So if it's 2.35, we can just round up the number. Let's say the poles should be located near 2.4 plus minus negative 2.4 plus minus J 2.4. Roughly, roughly around this point. And if it's roughly at this point, we can even calculate Kp. Actually, still approximate. We do the following. We know for sure that if we find the exact location of the pole, I can plug that into the characteristic equation. And this should hold. But since this is negative 2.4 plus minus J 2.4, it's just something I approximated. They may not be the precise location. So if you plug in one of these two complex poles in this equation, you may not have a real number being K. And to help us with or to overcome this problem, so first of all we can rewrite it as minus 4s plus 3 here, and then s plus 2, s plus 3. This is 0.3. So as I mentioned, well, if you have the exact location of the poles, you plug that into this Kp equation, K will be absolutely a real number. But if you're going to put in an approximate location, KP calculated from this equation may not be real. And to overcome this problem, we're going to do that. We're going to say, well, KP is going to be a real number since it's on the root locus, right? You have this K on the root locus. You have this on the root locus, and you want this to be a positive number, so KP has to be positive. And if KP is positive, what about I add absolute value here, absolute value here? So I don't really have to do the absolute value for KP, since KP is positive automatically. Right? So this will be approximately equal to negative 2.4 plus J 2.4 absolute value. This is the absolute value for the first. And then 0.4 to plus 2 will be, and then plus J 2.4. This is the second. And then 0.6 plus J 2.4. That's the third. Divided by 4. I take the absolute value again. It is minus 2.4 plus 0.3. How come 0.2 here? So 0.3 here, and negative 2.1 plus J 2.4. So replace everything with absolute value when we do the approximation. But again, if you have the precise location of the poles when you plug this in, KP will be positive, like the one we did in the P controller. Okay, this is exactly what we did. We plug in this exact location of the poles into the equation, and you have K being a real number. But when it's approximate, doing the absolute value will be the right way to do. And this would be 1.6. Roughly 1.6. And again, so if you want to have an initial design of your controller, then your controller will be 1.6, 1 plus 0.3 over S. Or just 1.6 plus 0.48 divided by S. And you should know that this is your initial design. You need to check the overall system behavior and make sure everything checks out, because we do this calculation approximately. There may be some errors, maybe it's not 100% correct. So you need to do all the calculations appropriately after that, just to check. So this is one. And if you compare what we have in the previous case, you can see adding this additional pole and 0 actually bend the root locus a little bit, okay, compared to 2. And the way to minimize that is to keep this pole and 0 as close as possible to each other. And the ways to keep them as close as possible to each other is to choose this Ki over Kp as small as possible. Okay? So choosing a small number will help you retain the shape of the root locus similar to the one that you only have a P control. And this is will be the process to do this.